Okay, in this video we will be looking at a final exam review, and we'll do that by looking at the spring 2012 final exam that I gave. Now in the spring we have a 2-hour final exam, hour and 50 minutes, and so it was done in 1 day, where your final exam will be done in 2 days. I have posted the clean copy of this exam on the online classroom site as a final exam example. It does not have the solution on it, and I'm not going to crunch through all the numbers right now. I looked to see if I had the solution printed out somewhere. I don't have it at my home this weekend, so I'll probably post the solution Monday morning when I get to school, but we'll sketch out the solution. I'm just not going to crunch all the numbers for you today. And so I would hope that what you would do is first go and get that exam and spend about 2 hours attempting to take the exam, and then only after you've spent that time taking the exam would you then come back and listen to me explain the solutions, and then you can take a look at the numbers that will be posted on the online classroom site. So go print out your own copy of the exam, pause the video right now, and take the exam. And so I hope I'm saying welcome back to everybody who has attempted to take the exam, and you've learned a bit about what you do and don't understand, and you'll learn more by hearing me explain these problems. So here we go. First problem. Notice it's a 10-point problem. There's some 10-point problems on here and some 15-point problems on here. So this is the 10-pointer. So we have a stunt car driver is attempting to drive her cart over a stack of container boxes. She must attain a peak height of 20 feet. To safely clear the containers, she'll use a 10-foot tall ramp with the ramp angle set at 45 degrees. Write a 3 unknown set of equations that could be used to solve for A, the minimum speed she must reach to achieve at the top of the ramp to successfully reach the 20-foot peak height. The required location of the center line of the containers. So what speed does she need here? Where do we place the containers, and how much time does it take for her to travel through the distance R? Okay, and so clearly this is a ballistics type problem, which is the constant acceleration equations on the front side of the equation sheet, and we have both a position equation, a velocity equation, and an ADS equal VDV equation. So these are the equations for the most part that we have to work with, and I will be applying those equations. One thing to notice right away about this problem is that it is a height limited problem. At a key point in the problem, that is where we want our peak height to be, and anytime we see that, that means we're probably going to be writing a peak velocity equation. And so I'm going to say velocity in the y direction, with y direction being up. That's the equation that I'm going to write. And so I'm going to say V final in the y is equal to V0 in the y plus the acceleration times time. And then that one needs to be fleshed out a little bit, in that the V final in the y is 0 and the acceleration is minus g. And we're working in feet and pounds and seconds, so we'll put in the appropriate term there. And then this V0y, the y component of V0, is going to be either sine or cosine of 45, and it doesn't matter since it's 45 degrees. So the actual equation that we will be making progress with is 0 velocity when we reach here is equal to a V0 sine 45 degrees minus 32.2 times time. And that's one equation, but it has two unknowns in it. It has V0 and time. They're both unknowns, and so we have one equation, two unknowns. Let me zoom out a little bit, give myself just a touch more room to write on this thing, so that I'm writing large enough for you to read it. Okay, so this would be V in the y direction. Now let's do position in the y direction, and we'll say that the S final is equal to the S in the starting position plus V0, this is the y direction, again positive here, V0y times t plus 1/2 at squared. And we know that our S final is 20, our S0 in the y direction is 10, and our V0 we'll have to write, and we know that the acceleration of gravity will apply. So we're going to say that 20 is equal to 10 plus V0 sine 45 degrees times time minus 1/2 32.2 t squared. And here we have another equation. Let's put an arrow. That's not an equal sign, that's an arrow. And this equation, we would have V0 and t as an unknown, and that actually makes it a two equation, two unknown set, so we could solve that directly. And the third equation of the set that will bring in the distance r is we will do s in the x direction, so that would be in the positive direction that way. We'll write our position equation as S final is equal to S initial plus V0t plus 1/2 at squared, and our starting position is 0. Our final position is called R. Let's slide that up a little bit. And we have a V0 that will become, let's see, this is V0x. So V0x will become V0 times the cosine of 45 degrees. And this is going to be 0 because we don't have any gravity acting in the horizontal direction. And so this equation produces R is equal to, we won't write that 0 down, V0 cosine 45 degrees times time. And then I'm going to put this plus 0 right there to remind us that we had that acceleration term. And this is our third equation, and it's going to involve R and V0 and t from the original set. And so a total of 3 equations, 3 unknowns, all totally solvable, and 2 of the equations are solvable as a 2 equation, 2 unknown set. And so then it's just a matter of crunching those numbers. That is problem number 1. Problem number 2. We have a pickup truck. It's traveling at 50 kilometers per hour. It's going to apply its brakes hard, come to a stop, but we do not want to allow that crate to slip. So the question is, how hard can he apply the brakes, or determine the acceleration and then determine the distance that he can come to a stop in. Okay, and so what we'll do first of all is free body diagrams. We have the crate, and the crate is going to have an acceleration. We're going to call that acceleration, we'll just call that direction positive in general, and we're going to have mg acting downward. We're going to have a normal force acting upward. We're going to have a friction force that's going to resist the block sliding toward the left. Okay, and I think we will also call, let's call up the positive direction. Okay, and so what we can say is sum of forces on the box is equal to mass times the acceleration of both the box and the truck. And we will write this in the vertical direction, and so we will have minus mg plus n is equal to 0, which gives us the trivial and obvious equation that is n is equal to mg, the weight of the box, and let's see, that's a 300 kilogram crate, and so n is equal to 300 times 9.81 meters per second squared. We'll slide that over a little bit so you can see that. That takes care of sum of forces in the y. Sum of forces in the x direction on the box is equal to mass times the acceleration. Let's see, and this one was 0, so we'll write that one in. No acceleration in the y. And so we will have only a horizontal direction force, which is our friction force, which is mu times n. And so we will have a negative mu times n is equal to mass times the acceleration in the x direction. And therefore the acceleration in the x direction is equal to minus mu times the normal force divided by the mass. And we all know all of those numbers, and we can plug that in. So we have the maximum acceleration that will allow us to come to a stop without allowing the crane to slip, and that mu is a 0.3. Okay, having just looked up above to check the value of mu. Okay, so now we know the acceleration, and knowing the acceleration, we can determine the distance to come to a stop by using our constant acceleration equation in the ADS equal VdV form. V final squared equal the initial velocity squared plus 2 times the acceleration times s minus s0. And so we will say that, we'll just write the generic equation down. V final squared is equal to V initial squared minus 2a delta s, and V final is 0 is equal to, and our initial was 50 kilometers per second. Kilometers per hour. Okay, so let's go ahead and turn that into, let's see, we want to determine the shortest distance. I think we'd probably like to determine that distance in meters, and so let's turn kilometers by multiplying by 1,000. That will give us meters, and then for hours, if we want meters per second, then we would divide by 3,600, which is 60 times 60. Okay, so this is our final velocity, initial velocity, quantity squared is equal to, let's see, minus, I wrote the equation down with a minus sign here. I'm going to put it down generically as a plus sign because that's the equation given to us, but we need to think through the sign. Okay, and our acceleration as given in this diagram, our acceleration is a negative number, so we're going to be plugging a negative number in here, so we're going to leave that as a plus 2 times ax, which is negative, times our distance that we can come to a stop, so delta x. And at this point we know our velocity stuff, we know the acceleration from here, the only unknown is that delta x, and so we'll solve, and this problem's over. Problem number 3 has a hemispherical surface and a box or a block sliding down that hemispherical surface, but there is and it's a perfectly circular surface, and we have a perfect rope of perfect radius to hold the block on the hill. So this says we have a 3-pound crate released from rest up at the top when theta is 90 degrees, begins to slide down the frictionless 10-foot radius circular slope. A 10-foot rope forces the crate to remain in contact with the circular surface. Determine the force in the rope when the crate reaches point A at theta equals 0 degrees. Neglect the size of the crate. Okay, so we know the speed of the box at the top, and that was given. And we're going to presumably want to know something about velocity when we get here. And the key thing is determine the force in the rope. And that force in the rope is going to be in the normal direction at all times. So we're going to be saying sum of forces in the normal direction is equal to mass times acceleration in the normal direction is equal to mv squared over radius of curvature. I've suggested you never stop writing this equation until you get to here. And since we're interested in this equation at that point, we're going to need to find the velocity at point A. Knowing the velocity up at the top looks like a very nice energy problem. And so we're going to solve an energy problem followed by a sum of forces in the normal direction type problem. And so energy conserved, T1 plus V1 is equal to T2 plus V2. And we will have some starting T1. We'll have some starting MGH. The rope does not stretch, so the rope does not store energy. Our surface is frictionless. That's why we have a conservation of energy equation. And we will end up with an increase in our speed. And I would say that we have no V2 at the bottom because that'll be the potential energy reference. And so writing the energy equation, we have, what do we say for an initial velocity? 3-pound crate. Oh, it is released from rest. Okay, I forgot. I was thinking that one had initial velocity. Released from rest. Okay, so that's 0. Then we'll have our kinetic energy. So M times G times H, and that H is 10 feet. And T1 is 0 plus MGH is equal to 1/2 mv squared plus mgh, but that h is equal to 0. And so we have our initial mgh becoming 1/2 mv squared. And so this is a one equation, one unknown problem, and we get that v is equal to, and I guess I'll go ahead and do the algebra, 2 mgh over, let's see, that's v squared, is 2 mgh divided by m, and the m's cancel, which says v is equal to the square root of 2gh, and we're not seeing that equation for the first time. So we can get our initial velocity, our final velocity out of this thing. And then on our diagram, we would have a free body diagram. We have the box having reached 90 degrees on this curve, and we have mg acting downward, and we have a rope force presumably acting inward, and our rope has basically replaced the normal force, allowing us to have a normal force that actually pulls the box in. And so those look like the only forces that we have happening here. And so we can say in the normal direction we would have a, let's see, we're going to call that, we'll just call that N, the force in the normal direction. So sum of forces in the normal direction is equal to mv squared over rho, and our only force in the normal direction, where we would call this E sub n plus, would be normal force, because we are down at 0 degrees, gravity doesn't contribute, so the normal force is equal to mv squared over rho, and we know v, or v squared, from earlier. We know the mass, radius of curvature is a constant of 10, and then so we can find the force in the rope is the normal rope. Force in the rope, and I didn't slide down, so let's start over. From the free body diagram, sum of forces in the normal will be a positive n, is equal to mv squared over rho, and that is a rho. So normal force equals mv squared over rho. We know m, we know v. Rho is the 10-foot radius. So we can find the force in the rope almost instantly. Okay. A 200-gram bullet is fired toward the center of a 15-kilogram wooden block. The block rests on a rough 20-degree sloped surface. The bullet enters the front of the block with a velocity of 900 meters per second and exits the back of the block at 300 meters per second. So this is not precisely an impact because we don't have embedding. This is not a momentum trap. It's not a hit and stick. It's not supermassive difference. It's just an interesting momentum problem. Okay, coefficient of kinetic friction between the block and the surface is 0.4. Determine the distance the block slides up the slope before coming to a stop. The key thing is we know what happens to the bullet as it passes through the block. It goes through a momentum change. And so what we can do is, rather than writing conservation of momentum for the bullet block pair, which is true, we're going to focus on the bullet itself, and we're going to say that for the bullet, mv1 plus the integral of f dt is equal to mv2, and if we're going to declare positive up the hill, so we'll say that m times 900, and then our force acting on the bullet, if we were to draw the bullet free body diagram, we would have friction force, oops, that's an F, lowercase f. We'd have a friction force acting to the left on the bullet, and to the left is going to be negative, so minus, and this integral f dt is equal to mv2, and v2 is 300, and we know that the mass is 0.2 kilograms. 200 grams, 0.2 kilograms. Okay, the only unknown in this problem is the impulse. Okay, and so we'll be able to say that this integral f dt, the impulse, is going to equal mass times 900 minus mass times 300. That's the impulse that the block has applied to the bullet, and we will solve for this impulse. Once we have solved for that impulse, we'll understand that that's the same impulse that the bullet applies to the block. So now we will look at the block, and we will look at impulse momentum for the block and say that mass times v1 plus the integral of f dt is equal to mv2, and for the block v1 is 0 and v2 we don't know, but we do know the impulse now, and so v2 would be our only unknown, and so we can solve for v2. Now that we know the change in, now that we know the speed of the block right after the bullet leaves it, we can now do an energy problem to figure out how far the block goes up the hill. And so for the block, we will have a 1/2 m v2 squared, and that's its velocity right after the bullet is left and before it has traveled any distance. Okay, plus mgh is equal to 1/2, let's see, we're going to, this isn't conservation, this is we have a work term, plus the integral of f dot ds, that would be our friction term, is equal to 1/2 mv3 squared plus mgh3, and no spring terms or anything like that. We are starting from the velocity right after the impact, v2, which we know. This is the lowest point in the problem, so let's call that h equals 0, and we will simply leave that one alone as an h. And this v3, let's see, we said where does it come to a stop, is that right? Distance the block slides up the slope before coming to a stop, and so that term goes to 0. And so what we'll have left is a 1/2 m v2 squared, and we know the v2, plus our friction force times s, the distance that we're going to travel up the slope, is equal to mg. Now let's look at our height term, because the height is going to be related to this s. We have what kind of a slope? It's a 20-degree slope, so our height is going to be s times the sine, that's an s, times the sine of 20 degrees. And our friction is going to be a mu times n thing, and so let's just deal with that. Friction is equal to mu times n, but when we sum forces in the y direction, n is going to become mg, and let's see, so it's going to be an mg cosine of 20 degrees. And so we will plug all of this in for f, and the only unknown in this equation then will be the value of s, and we solve for the value of s at this point. Again, I'll have those numbers crunched for you on another document that I upload in the morning. There's problem 4. Now, let's take a look. First of all, first four problems were basically chapter 12 was ballistics, chapter 13 F equal ma, chapter 14 mostly work and energy with a little bit of normal tangential, and this was chapter 15 with a little bit of chapter 14 on it. So this is impulse momentum of the block and the bullet, to learn what we can about the impact, followed by a work energy problem. So chapters 12, 13, 14, 15 in order. Was your test guaranteed to be that way? No, but I did say that I would tell you which chapters would be covered each day on the test. It probably won't necessarily be in this order. Okay, but we have taken a look at each of the first 4 chapters, and those dealt with particles, and now we turn to rigid bodies. And so, in this problem, a 15-pointer, it says, at the instant shown, velocity analysis of the systems reveals that the small wheel at B has a velocity up the slope of 10 inches per second, and that the 20-inch rod AB has an angular velocity of 0.354 radians per second in the counterclockwise direction. So we know V equals 10 that way, and we know that counterclockwise direction, this rod has an omega equal 0.354 radians per second in the direction shown. Okay, if at the instant shown point B also has an acceleration of the slope of 3 inches per second squared. So A equals 3 inches per second squared. Determine the angular acceleration of the wheel. Okay, and so we're going to want to know, let's see, right hand rule positive would be counterclockwise, and so that would be an alpha question mark. We want to know the alpha of the wheel. Okay, the 6-inch radius wheel is pinned to the end of the rod and rolls on the ground here without slipping. Hint, first find the acceleration of point A. Now, looks like the velocity problem has been done for us. We don't know omega of this wheel, but we may or may not need the omega of this wheel, and if we do, we'll go get it. So let's go ahead and start with the hint. It says find the acceleration of point A. So the acceleration of point A is equal to the acceleration of point B plus some alpha cross R plus an omega cross R. And now, what body are we talking about? We're talking about body AB, and this would be of R of A with respect to B. Same here, A with respect to B. And so this will be an alpha AB, an omega AB, an omega AB. And so now we know the sense of everything, and the acceleration of B is a vector, and it is 3 meters per second up the 45-degree slope. And so here's what we're going to say. The acceleration of A, let's go ahead and write this as a vector. And if we look at point A is at this instant traveling purely to the right. Okay, it is not traveling on a circle. That point A travels on a straight line always. So we have the acceleration of A in the x and 0, and we're going to let positive be these directions for x and y. Okay, so the acceleration of A, we will take into account that we know that it travels on a straight line because it's always a fixed distance from that straight line. And then we would say the acceleration of B, which would be a 3 times, and it would be, let's see, the horizontal term would be the cosine of 45 degrees and the sine of 45 degrees. Those don't really matter which is which. That would be the acceleration of point B, totally known. And let's just make note over here that R of A with respect to B is equal to, A with respect to B is going to be a minus 20 and a 0 at this instant. So to go from B toward A, we'll travel 20 backwards in the x direction. And so this is going to be a plus alpha AB cross product. So I'm going to do the scalar multiply with the 0 and minus 20, and we'll put that minus sign in front of the 0, which is irrelevant. And then omega cross R becomes minus, and what is omega AB? That was given to us. Let's label this as an AB, is equal to a positive 0.354, 0.354, so minus omega squared times R of A with respect to B, no flip-flop, minus 20 and 0. Okay, and in this equation we have two equations, upper equation, lower equation, or the x equation, y equation, and we have the acceleration of point A in the x direction, and we have the alpha AB as unknown. And so we can solve the two equation, two unknown problem. I don't have those numbers handy right now, but I'll get them to you tomorrow morning. But AX and alpha AB are known. Now, if I want to, I could write this out in vector form, and I think I will, and say that the acceleration of point A from the point of view of, let's call this point C, is equal to, let's see, do we really want to do that? This thing, we can, actually, this is going to be more complicated than it needs to be. I'm going to write it out anyway. Is the acceleration of point C plus some alpha cross R minus some omega squared times R. We'll take that liberty at this point since we've done it before. And the acceleration of A will now be an AX and a 0, but this is known, is equal to the acceleration of C, ACX, ACY, plus alpha, and we need to put some subscripts on this, sorry, alpha AC, omega AC, which we have not yet solved for. So I'm going to keep writing the equation out, but there's going to be a shorter way to get to this without us having to solve for this omega, which is going to be troublesome, possibly. Okay, so unless it may turn out to be just as easy. So minus omega AC squared times, now we got to decide what the R is, and this R is A with respect to C. A with respect to C. And we might as well write that out, that R of A with respect to C is equal to, we only travel in the vertical direction, and so it is a 0 in the X direction to go from C to A, and it's a positive 6 inches to go from C to A. Okay, so this is, oops, alpha cross R minus omega squared R A with respect to C. And this is an alpha AC, which is what we were looking for. Let's double check that. Where's the determine the acceleration of the wheel at the instant shown. Now, what I was getting at on the easy way is, if I know the acceleration of the center, I know that the acceleration in the tangent direction is here, and so the acceleration in the tangent direction here for a wheel that rolls without slipping would let us say that acceleration of point A is equal to R of the wheel times alpha. Given that that tangential acceleration is 0, yes, there's normal direction acceleration, we'll ignore that. So we can get the alpha as soon as we know the acceleration of A, which we're going to know right here, because we're going to solve it from this equation. But let's see if this falls out as being this simple, and even though we don't know omega AC. Okay, and so this is going to be the acceleration of A in the X, 0, is equal to acceleration of C in the X, but we know that that is 0 because that's the tangential acceleration of point C. The normal acceleration would be ACY, so there's a 0 there, plus alpha, scalar multiplying the 6, 0, and put a minus sign there. So we've done the vector flip-flop. Then minus omega AC quantity squared, 0 and 6. And so let's see how this turns out. Our top equation, which is the x equation, is going to say the acceleration of A in the x, and that's known, is equal to that 0 minus 6 alpha minus omega AC squared times the 0. And since that term goes to 0, that term is a 0. This top equation gives us exactly the equation that we were deducing from the kinematics ourselves, that the acceleration of A in the x direction is an r alpha quantity. The r is 6, and so we can solve directly for the alpha without actually needing to compute the omega AC quantity. And so that problem is over. And we really didn't have to go through this step right here, because this step could have been replaced quickly by that step, and they end up saying exactly the same thing. If I remember right, believe you've seen this problem before. Okay, so we have a 10-pound wheel, radius of 8 inches, radius gyration of 4 inches. It rolls down the 30-degree inclined slope without slipping. Determine the tension in the rope connecting the 2-pound block and the wheel. Now, this would be a very good point to pause and say, is this either an energy or a momentum problem? And the answer is neither. And the reason is a good energy or momentum problem would have two different locations of interest. And this one simply has the right now. And the right now is always true as this thing moves, because it moves with constant acceleration. But there is no velocity now and velocity later where velocities matter between now and later. There is only the right now. That makes this automatically a Chapter 17 problem if we have mass in that big wheel, which we do. So this is a Chapter 17 problem. Obi-Wan says cut the rope and draw the free body diagrams, and so we will do that. And so we have the 2-pound block, and we have tension acting upward on that block, and this small pulley is massless because nothing is stated about it, and so it's not going to change the tension. And we have a weight of 2 pounds acting downward, and we can then say we can do a sum forces equal mass times acceleration. And I'm going to declare that up is positive for a very good reason that we'll see in just a second. And then for the wheel, we have the wheel heading down the slope, and we have gravity in the quantity of 10 pounds acting that way. We would have a normal force. Let's see, rolls without slipping. So in fact, we probably don't care about the size of the normal force. We will have friction acting up the hill, causing this thing to rotate in the right direction. So friction acting up the hill, and we will have rope tension acting up the hill, and these two are the same tension variables. And I'm going to declare that positive and that positive. As the wheel heads down the hill, it will rotate that way. And now the choice that I've made is a coordination between the acceleration of the wheel, the alpha direction of the wheel, and the upward motion of the block. Those can all be positive for this device moving under the constraint of the strings. So if I write kinematic equations, then I don't have to worry about signs. I can leave the entire kinematic equation positive. Okay, and so I am interested in let's see, determine the tension in the rope is really all I'm after. Now in the end, I'm certain I'm also going to end up finding the acceleration of the block, maybe the acceleration of the wheel, and certainly the alpha of the wheel, depending on where I choose to some moments. So let's look at the equations that we have available, and this is from chapter 17. And the equations that we have available is sum of moments equal I alpha, either about a fixed point or a center of mass, or we can sum moments about a arbitrary point, or we can sum moments about the center of gravity. I'm going to sum moments about the center of gravity. It may actually make the problem one equation, one unknown longer, but we'll deal with that anyway. So let's deal with the block first and say that sum of forces on the block in the y direction is equal to mass times the acceleration of the block in the y direction. And that the acceleration of the block is only in the y direction, so that we don't need to call it that. And the force acting on the block is going to be a T positive minus 2 is equal to mass times the acceleration of the block in the positive direction, and I let my signs go according to that plus sign. And then we'll worry about the wheel traveling, and so we will let down the slope be positive and say summation of forces on the wheel is equal to the mass times the acceleration of the wheel, and that will then produce our forces acting on the wheel in the downhill direction will be a minus T plus a component of gravity, which is going to be a 10, and our slope angle is measured here, 30 degrees. Okay, and so our gravity force down the hill will be mg times the sine of the 30 degrees. Okay, we have tension acting up, we have gravity pulling us down the hill, and then we have, and so the gravity is positive for this sine system, and then we have minus our friction term is equal to the mass times the acceleration in the x direction. And looking at this equation, let's go back. We have tension and the acceleration of the block. One equation, two unknowns. This one, we bring in tension, we bring in friction, which is new, and this is our acceleration of the wheel, a new unknown. So now we have two equations, four unknowns. That's not looking very good. Okay, and so now let's go with summing moments about the center of gravity. And we're going to do this direction positive. Summation moments about the center of gravity is equal to Ig alpha. And so looking at our free body diagram, moments about the center of gravity will simply be our friction term. The normal passes through, the rope tension passes through, gravity passes through, and so we're going to have plus friction times, that's a friction force, times the radius of the wheel is our only moment term, is equal to Ig alpha. And in this one we have unknowns. Friction, the radius of the wheel we would know, the Ig we'll know shortly, and the alpha is unknown. Wow, this thing is really building up. We have three equations, five unknowns, and what's going to happen is we're going to write two more equations and they're not going to enter any new unknowns, And we've really said everything we could say about the bodies from our fundamental equations. Sum of forces here, sum of forces here, sum of moments here, 3 equations, 5 unknowns. Now the 2 kinematic equations that we can write, looking at this picture, if we were to write a rope equation, we would see that the acceleration of the block equals the acceleration of the wheel. And if I define up as positive and down as positive, those are compatible. So A sub B equals A sub wheel. And that is our 4th equation. It involves unknowns, A sub B and A sub wheel, but those are not appearing for the first time. And then finally we can write our kinematic equation is that the acceleration of the wheel is equal to the radius of the wheel times the alpha of the wheel. And this is our 5th equation, and it involves A of the wheel and alpha. None of those appearing for the very first time. I guess you couldn't see me write that equation. The acceleration of the wheel is R alpha. And so we now have 1, 2, 3, 4, and 5 equations and 5 unknowns. Solve them for, in the end, solve them for rope tension, which is what we were asked for. Okay, problem number 7. Pause. Pardon me while I take a sip of coffee. It's just about nap time on Sunday afternoon while I'm doing this, so forgive me. All right, we have a double radius pulley pinned to ground here. It weighs 30 pounds, has a radius of gyration given. There's a 20-pound weight hanging from the rope. At the instant sewn, system is held at rest, and the spring is in its unstretched length. So that spring is at its free length. When the system is released, allowing everything to move, determine the velocity of the weight after it has fallen 1.5 feet. Okay? And so, boy, this, as soon as we see a spring, we got to be thinking either the F equal ma type chapter, but that's unlikely. We really have to be thinking energy when we see springs. That's not always true, but it's often true. And so the question now is this a conservation of energy problem? And it is. There's no human interaction. There are no friction losses. So this is a conservation of energy. So we can say T1 plus V1 is equal to T2 plus V2. And we are starting from rest. So that goes to 0. Our spring energy might be 0 to start, but we might say we have some gravitational kinetic. That's up to us. T2 is going to have 2 pieces from the disk and the block, and V2 will have spring energy but no block energy. And so let's start this thing off. So we have a 0 for the kinetic energy. The V1 is going to be mg, now let's see, times 1.5, and this is m of the block, mass of the block. Let's see, and that's a 20-pound weight, so that's going to be 20. All of that's going to be 20 times an initial height of 1.5, because it's going to fall that far later on in the problem, plus 0 for the spring. And let's go ahead and put a 0 there, and this is our T1 value. So the only energy we have to start the problem is our gravitational potential energy, mgh, will give it a start. And then on the other side, we're going to have a 1/2 mass of the block, velocity of the block squared, 1/2 mv squared, plus 1/2 I omega squared, and this will be an Ig omega squared. That will take care of the kinetic energy. and then we will have plus mgh, but that h will be our zero value. That'll be my gravitational potential datum. And then finally the spring, so plus 1/2 k times stretch squared. Okay, and so the unknowns that we will have in here, we want to know the velocity of b. Omega is going to be an unknown, and right now the stretch in the spring is an unknown. So that looks like one equation, three unknowns for VB, omega, and stretch. And so we're going to do a little bit of kinematics to deal with these three unknowns. So this is one equation and three unknowns. All right, now we can relate the omega of the disk to the velocity of the block, and that VB is equal to R big times the omega. And this one will involve this one will involve VB and omega, but they're not showing up for the first time. This is our equation number 2. And then finally we need to relate the stretch in the spring to the travel in the block. Okay, given that both devices will undergo the same angle change, delta theta. And so by using the equation that delta S is equal to R delta theta, and recognize that this delta theta pertains to the spring and to the block. They share the same delta theta, and so what we can say is delta S over R for spring, and this would be R small, is equal to the 1.5, that's the delta S of the block, divided by R large. Okay, this is our third equation, and this delta S of the spring, also known as stretch, so we'll call that stretch, will involve the unknown stretch, and that's the only unknown that it will involve. But sorry, it's not showing up for the first time, which means we can solve for stretch, or we could treat this as three equation, three unknown set, but this one is a one equation, one unknown solvable. Then we'll make a substitution here into this one to solve for the rest of the numbers in the problem. That was a chapter 18 problem. You might guess that this is a chapter 19 problem. So we have a double pulley with a weight hanging on it, radius gyration given, 2-pound weight hanging at B. The outer rope is pulled with a time varying force. It is not a constant. Where T is measured in seconds, P in pounds, determine the velocity of the weight at B when T equals 1.5 seconds after the system is released from rest. Strong hint, use an impulse momentum method, and this does not say conservation of momentum, because we clearly have a human interaction here, a human impulse. Okay, and so we can work this one a couple of different ways. Going back to our equation sheet, we can certainly talk about angular momentum. So our starting angular momentum is equal plus the angular impulse is equal to our final angular momentum, and if we want to, we can deal with the angular momentum of the system, including the weight, by bringing in the linear momentum of the weight and taking its moment about a key point will give us the angular momentum of the weight. And that might make it a one equation, one unknown problem instead of a two equation, two unknown problem, possibly. Let's go ahead and try it that way and see how it turns out. The other alternative is to cut the rope, and we might just talk about that one briefly. And so we're going to say h0 plus the integral of m of t dt is equal to h1. And are we starting from rest? Please shown. 1 seconds after the system is released from rest. And so our starting momentum is that. And we will have to deal with our angular impulses. And we will have two. This one is going to be the gravitational weight of the block. That pulley weighs 10 pounds. There's a 2 pound weight acting down, and this P is 2.5 T. And so we're going to have two impulses which cause an angular motion. We believe that weight is going to be moving downward, so let's go ahead and call a moment in that direction positive. And so let's deal with these integrals. We're going to have a plus 2 pound weight acting at a moment arm of 0.75 feet and acting through a time of 1.5 seconds. And so this would be the integral of m. These two pieces are m, but they're constant, times dt. And then we're going to have a minus the integral from 0 to 1.5, a 2.5 t, that's the force, times a distance of 0.75. dt. Oops, that's not good. Sure hope I can get that back and looking right. That's going to be close enough for now. I'll have to align it later again. And so these would be our two angular impulses. And then finally is equal to our IG omega of the disk plus the moment of this linear momentum. So plus the mass of the block, velocity of the block, that's the linear momentum, and we want the moment of the linear momentum, and that's acting through a distance of 0.75. Let's see, seems like I got one of these distances wrong. Yes, this one's actually acting at a distance of 2 feet. 2 feet given here. Okay, let's assess and see where we stand. We are going to have to integrate this constant times t, which is going to become a t squared over 2 type term. Nothing unknown here. There will be nothing unknown there. And we will not know omega. And we will not know v sub b. But we do have the kinematic equation that says v sub b is equal to r small times the omega, and these will have the same unknowns in it. We know the value of r small is 0.75 feet, and so now we have two equations, two unknowns, and we will learn the omega and the velocity of b. And what were we asked for? Determine the velocity of b when t equals 1.5 seconds, and we will have done that. That takes care of this final exam sample. Like I said, I will post the solution to this one when I get into the office on Monday morning. I'll post that solution. I've already posted the problem statement on D2L for you. And then we will have a quiz on Monday morning, and then on Tuesday I'll do a review again, probably look at a different final exam with you, and then we'll have Wednesday and Thursday exams. So I'll see you on Monday morning.